Okay, the last thing, this is the mathsy bit, so I'm going to wipe off the stuff I've got there. We're going to use the example in the book actually, so we're using Continuing Chemistry, page 193 to 194, where they've got a methanoic acid methanoate buffer, and we'll use that one as our example. So the question states, what mass of sodium methanoate, which is the conjugate base, what mass of sodium methanoate must be added to 1 litre of 1.0 moles per litre methanoic acid to make a buffer of pH 4.5. It also gives us our pKa. I'm just going to write down the important information up on the board now for you. So we know that we've got 1 litre of 1 mole per litre methanoic acid. So we know that the HCOOH, 1.00 litres, 1.00 moles per litre. And I also was told the pKa, and the pKa is 3.75. So I'm going to do something really fast with that. I'm going to say that Ka equals 10 to the power of negative 3.75. It's not a real number, that. I'd have to press equals on my calculator, but I can work with that for now. Okay. The other substance we were told about is that we want to find the mass of sodium methanoate, which is HCOO Na. So we're going to need a molar mass for that at some stage if we're looking with mass, because whenever we have mass and these sorts of things, I'm going to need to know that sort of thing. Okay, so I'm just jotting down some stuff that I know. The other thing I want to put, and I'm going to put a big circle around this, is pH equals 3.75. So hydronium ion concentration, the desired hydronium ion concentration, is going to be 10 to the power of negative 3.75. Sorry, it wasn't 3.75, was it 4.5? Apologies. After a buffer of a pH of 4.5.
Is pKa still 3.75?
Yep, because the pKa is always true under standard conditions, which this is, for that acid. Okay? So this is my big bit of information that's really important. This is where things are different to working out the pH of a weak acid. It's the only place they're different. You already know the pH, so you already know the hydronium. And hydronium does not equal the concentration of the conjugate base. Okay? So, how do I start it? I start it just like an acid question. Think of buffers as special acids. Okay, that's my biggest bit of advice to you. Think of them like special acids. So I'm going to write this. Dissociating with water. Okay. I'm then going to write down what I know about everything that's in it. I actually know a lot about it. I know that this is 1 mole per litre because I set it up there, it was in the question. So I know I've got 1.00 moles per litre. The water's not relevant in this because we don't use it in equilibrium expressions. I actually know this one as well, don't I? Well, sorry, I'm going to find this one here. This is my unknown. This is what the question asked me to find. This is my X, my unknown. I actually know hydronium. It's in my big box here. We want this to have a pH of 4.5 so I can fill it out. 10 to the power of negative 4.5. And apologies for not using real numbers, but I find it easier. Now I can plug all of that into a Ka expression. I'm sorry, I'm going to skip a step here and just put the numbers in. I've said Ka equals 10 to the negative 3.75, so I'll write that. That equals this times this over this. So it equals X times 10 to the negative 4.5 over 1. Well, that's not too bad, because 1's a nice easy number to work with. So, rearranging that to make X the subject, it's going to be that times that, so 10 to the negative 3.75 times 1, divided by 10 to the negative 4.5. So I've rearranged it. So now all I have to do is solve, and my maths is not too bad for this because I know how to work with things that are to the power of. That times 1 is that. Negative 3.75 minus negative 4.5 to me is 0.75. So my answer is going to be 10 to the 0.75. Not a real number, so I'm going to put that in my calculator and press equals, which is what I'll ask you to do now, please. 10 to the power of 0.75. 3 significant figures, please.
5.62.
5.62 times 10 to the anything, or... Okay, moles per litre. Okay, so 5.62 moles per litre. Now I've got a concentration, and I know, and I look at my data here, I can find out how many moles I need of it, and that will go into there. Once I find my molar mass, I multiply those two to find the answer to the question. So what I've done, the only difference between finding the unknown in this one and the hydronium ion concentration and then the pH of an acid is that I already know the pH. So there's no square root or anything like that. I've actually only got one unknown, the conjugate base. So just to work through that to finish the video off, this says there's 1 litre, so there'll be 5.62 moles. I then do my addition of the molar mass of this with the sodium in it. With the sodium in it. The salt has sodium in it. So I go 1 plus 12 plus 16 plus 16 plus 23, and we get 68 for that. 68 times 5.62 tells me I need 382 grams. 382 grams of this to make a buffer that has got a pH of 4.5. Right, so the processes are ones you already met earlier in the unit. That's why I've learnt it in the order we've done it this year. Okay? You write out the acid dissociating with water, because it will make the conjugate, which is usually your unknown, and hydronium, which is the pH you know. So what we've done is this one here. The only difference you might get is you might be told the concentration of both the conjugate and the acid and be asked to work out the pH. It's the same process. Okay, the only difference is you'd have to do negative log of your answer, because X in that case would be hydronium ions. So that, in a nutshell, is buffers that you're going to be working on over the next 2 lessons, including some experiments, hopefully.